Streaming has started, Shritikanta. You may please start.
Yes, okay, sir.
Yeah.
Good evening, everyone. Last class, Satya sir has introduced this Lagrange equation. He has derived this from D'Alembert's principle. And I also have solved some problems in last class regarding how to find degrees of freedom for some simple systems. Okay. Today, we will solve few problems in Lagrangian mechanics, means how to find the Euler-Lagrange equation for the system. Okay, and before that, I will solve one problem which has many times came in CSIR. I just want to, that is related to this concept only. I will solve this problem. After that, we will take up few problems in Lagrangian. Okay, as Sir did not teach much in Lagrange, so we'll solve some few simple problems in Lagrangian. Before that, let me solve a problem which has come many times in these competitive exams like CSIR, NET, GATE, etc. Okay, let me note down the problem first. A particle of mass m, particle of mass m moves in one dimension in the potential V of x equal to kx to the power 4, where k is greater than 0. At time t equal to 0, at time t equal to 0, the particle starts rest at x equal to a. For bound motion, the time period of its motion is, for bounded motion, the time period of motion is, they are saying it will vary as a power minus half. Second, propose vary as a power minus 1, or is independent of a. Fourth one is not well defined. So I think this is one of the questions which has come in CSIR. I don't remember the year. Okay. So in this given problem, they are saying the particle is moving in one dimension where the potential energy of the particle varies as kx to the power 4. Okay. At time t equal to 0, the particle is starting from rest at x equal to a. Okay. Now, if we consider the motion to be bounded, that means after certain interval, that means there is a range within which the particle is allowed to move, beyond which it cannot go. Okay. So if the motion is bounded, then they are asking how the time period will depend upon x equal to a. Here you notice one thing, at t equal to 0, the particle is at x equal to a. That means they are saying the amplitude, this case, is a. Okay. So they are asking how the time period will depend upon amplitude, and this potential is a power law potential. That means it is the potential is in the polynomial form. Okay, for this kind of potential, they are asking how the time period will depend upon amplitude. Is the problem clear to you, or any clarification you want? Okay, so anyone of you tell how to proceed this in this problem first? What should be our approach? How we can solve? Any idea? Please speak. It may be right or wrong, that does not matter, but you should speak. Okay, any idea? Anyone wants to say how to proceed? Okay, so this problem, see, we have to first obtain the condition in which there will be possibility for bounded motion. Okay, now you see here the potential is only depend upon x. There is no dependence on time. So one can consider this system as conservative system. That means the energy of the system is not going to decay. Okay, energy is going to be constant. Okay, now if I plot the potential energy of the system, here the potential energy, that is V of x equal to kx to the power 4. Now if I plot this potential as a function of distance, so this will look like this. Okay, this is for kx to the power 4. In fact, if you plot any power law potential, the potential will be a parabolic shape. The difference is that if you go for higher power of x, the potential will be more flat at the bottom. Okay, and it will increase sharply when you go for larger x. That is what. At this position, it will be more flat. Okay, if the power of the potential is high. Now notice one thing. Suppose if I start with energy, this is my V of x. Now if I start with initial energy of the particle as E1, let us say. Now my energy in classical mechanics is equal to your kinetic energy T plus V, where T is kinetic energy and V is potential energy. Now if I start with energy E1, you see, let's say, let us this point, let me tell us x1 and this is at x2. Now, when the particle is in this region, between x1 and x2, okay? If the particle is between x1 and x2, in those cases, the energy, you see that here the energy is E1 and this E1 is constant because the system is a conservative system. Now, in this region, the energy of the particle is greater than the potential energy. Okay? This is one Desjardins condition. In classical mechanics, your total energy must always be greater than potential energy. If the energy is less than potential energy, what will happen? If energy is less than potential energy, then your kinetic energy becomes negative. And this is not allowed in classical mechanics. Okay. So therefore, the region in which the the energy of the system is less than the potential energy. That is, in those regions, the kinetic energy of the system is negative. Those regions, we call them as classically forbidden region. Okay. So in classical mechanics, at all points, the energy of the particle must be greater than its potential energy. So this region from x1 to x2, it is guaranteed that the energy is greater than potential energy for all x. But when you go to this side, suppose you are here, this case, your energy, let's say this is x3. This point, let me name it as x3. Now at x3, if you see your energy E, this point E is less than V. If E is less than V, then what will happen to kinetic energy? The kinetic energy will be negative, and this is something not allowed in classical mechanics. Therefore, the particle in this case will constrain to move between x1 and x2, because beyond x1, that is left to x1 and right to x2, the energy of the particle is less than its potential energy, which is not allowed. Therefore, these regions are called classically forbidden regions. In quantum mechanics, the story is different. But in classical mechanics, at least in classical mechanics, these regions are not accessible by the particle. Okay. So they are called classically forbidden region. This is also classically forbidden region. Now, so all these points, they are classically forbidden. Only this region, they are allowed for the particle to move. So between x1 and x2, the particle will move. Now, you notice one thing: the particle, when it will come to this point, at this point, the energy of the system, that is E, equal to your potential energy of the system. Okay. So at x1 and x2, the total energy of the system is equal to its potential energy. Here also, because at this point at x1 and x2, at x1 and x2, your total energy, that is E1 in this case, will be equal to V of x. But what is that implied? I know total energy equal to T plus B. Okay. So if E1 equal to B of x, then kinetic energy, that is T of the particle, is 0. Okay. Kinetic energy 0 means the particle is at rest. Okay. So what will happen at x1 and x2? See, when the particle moves from here, the potential energy of the particle is keep on increasing. Okay. If potential energy is increasing, the kinetic energy will decrease, because total energy is kinetic plus potential. If potential will increase, then kinetic will decrease, so that their sum will be constant. Okay. So the kinetic energy will keep on decreasing, and at this point, the kinetic energy just becomes 0, so that the particle will not move further, and from this point, it will return back. It will go, and at this point, the particle will return back. Same thing will happen at x1 also. Therefore, these points x1 and x2 are called classical turning points. Okay, x1 and x2, x1 and x2 are called classical turning points, because in those points the particle will move back. Okay? They are called classical turning points. At those points, the kinetic energy kinetic energy of the particle just becomes 0. Okay. So due to this reason, the particle will not move forward and it will return back. And for this constraint, the particle will be allowed to move in this region only. Okay. Now suppose if you start with another energy E1, E2. If you start with another energy E2, that case your turning points will be this. Okay, like that. If you go to higher and higher energy, the range will slightly increase for the case of a power law potential. But always there will be certain region of space where the particle cannot move. Due to this reason, if you are dealing with a power law potential, there will be a bounded motion. That means the particle will move in a restricted region in space. Okay, so for a power law potential, but power law potential, one more constant is there. If you notice here, the potential will depend upon even power of x. It is square, fourth power, sixth power, eighth power. Okay, it should be in the form of x to the power 2n only. In those cases only you will have a bound motion. Otherwise, if you have an odd power like x cube or x fifth, in those cases you don't have any bound motion. Okay, so for a power law potential, that is where your v of x will go as x to the power 2n. In those cases, the motion will be bounded. Now, the question for you, can you tell me why we don't have bound motion? Why we don't have bound motion for potentials of the form where v of x will depend upon x power 2n plus 1, like in the odd power of x. Can you tell what is the region? We have seen for even power, this will have a bound motion. Can you think graphically and tell me why we don't have bound motion in case of a power law potential where the potential depend upon odd power of x? Can you just think and tell? Can you tell? Or if some of you wrote it in chat, I request Bhagirathi to read and tell. What is
Yes, sir.
or
Yes, sir. Sonal has told for x less than 0, all positions can be taken as for constant energy. Kinetic energy won't be negative.
kinetic
energy will not be negative.
For x less than 0, kinetic energy will not be negative. Okay.
Yes, sir.
Yeah.
And Arpita Aparajita Didi has said there is no global minimum.
Okay. Yeah. So this is correct. Okay. In fact, you notice one thing. For power law potential, we don't have any minimum. For odd power law, we don't have any minimum. Okay. Minimum is at infinity, minus infinity, and maximum at plus infinity for odd power. Okay. Whatever Sonal had told, that is correct. For example, if we plot x cube, then you see for x is greater than 0, you may have, suppose you start with this energy E, this may you have a turning point at here. But for x less than 0, you don't have any such points. Any region of space, at all points, your energy is less than potential energy. Your energy is greater than the potential energy. If you start with a positive energy. In fact, in negative energy also, if you start with a negative energy also, you will always have a turning points in the right hand side, but you don't have any turning points in the left side. So you will have only one turning points, but other side of the motion will be unbound. There is all regions in the space will be accessible by the particle. So you have to be careful for a power law potential where V of x depends upon the odd power of x. You don't have any you don't have any bound motion. Okay, so either in question they will give you V of x as some x to the power 2n or mod x power n. Okay, anything will be okay because all cases this is an even function only, so that doesn't matter. Either they will give you x to the power 2n or mod x power n. In both cases, the potential will have a minimum at x equal to 0. Okay, so the potential will have a minimum at x equal to 0. So therefore, for even potential only, we'll have such conditions. Now let us solve our problem and find the relation of time period with amplitude. We'll solve it for general case. Okay, we'll solve it for x to the power 2n. Then in our case, we'll substitute n equal to 2. Okay, I think what was there in the problem? We're supposed to find it for x to the power 4. So in our case, we'll put n equal to 2. But let us find it in general. So our starting point in this case will be from total energy, which is a constant of motion in this case, because total energy is, for a conservative system, it is constant. So the total energy E equal to half m x dot square plus k x to the power 4. And this E total energy, this is a constant of motion. That means this is not going to change with time. Now, my aim is to find this amplitude. That is, I have to find x as a function of time. How I can do that? This is a differential equation. X dot is dx by dt. So I have to integrate x and find x as a function of time. That's what I have to do. Okay. So if I do a bit simplification, what I will get, x dot square is 2 by m e minus k x to the power 4. Now your x dot, that is dx by dt, that equal to 2 by m e minus k x to the power 4 square root. So if I want to find x as a function of t, so I have to integrate this dx by square root of 2 by m e minus k x to the power 4 dt. This I have to integrate. Now the big question is, what is the integration limit and how to carry out this integration? These two questions we'll see. Now, notice one thing. Whenever there is a bound motion, if the motion is periodic, suppose we have a potential like this. Now, if this is my turning points, x1, x2, as the potential is symmetric, so I can consider this as minus x1 and this as x1. That means the point is equidistant from x1. The origin is equidistant from the turning points. Now you see, when I say one time period, that is, suppose the particle starts from here. When I say one time period, that means it will come back to same position from where it has started. That is, this will go from, if it starts from here, this will go back to there, and again it will come back to here. Now, the time required to move forward, that is to go from here to here, will be same as time required for this to come back to the position from where it started. So, like if you compare this with the motion of a pendulum, if you started from at one extreme point, one time period, it will be equal to the point from where it is started. Now, if it is at the mean position, it will go to extreme position. That is, this is the mean position, x equal to 0, to go to extreme position, that is x1. Okay. Now from mean position go to extreme position, the time required will be 1/4 of that. That is, if period is 4, period is t, then the time required for the particle to move from x equal to 0 to x1 will be t by 4, because total time period is constituted by 4 of this time. This is 1. While going and while coming back, there is 1. Here also 1 and here also 1. So 4 times, if you consider this motion x equal to 0 to x1, that will give rise to a full time period. So in order to carry out this integration, simply we will consider, in order to carry out this integration in a simplified manner, we'll consider our limit. Instead of considering from this point to this point, see, if I consider from minus x1 to x1, I have to consider this dt as 0 to t by 2. Now, if I consider from 0 to x1, the time required for this will be 0 to t by 4, 1/4 of the period. Okay. Therefore, I will rewrite this integral with limits from 0 dt. The limit will be from 0 to t by 4, and this limit will be from 0 to, one limit is from 0 to x1. x1 is the turning point or the maximum displacement from the origin. Okay, in the positive side, so let me denote it as some x plus. X plus is the maximum displacement from the origin, or you can call it the amplitude of the motion. Okay, because at x plus the particle turns back, therefore x plus is the amplitude of the motion. Amplitude of the motion. Okay. So 0 to x plus dx divided by 2 by m e minus kx to the power 4 square. Now here we'll apply a trick, because this case you see, my aim is to find the relationship between the time period and amplitude. Now, in order to find the relation between time period and amplitude, I have to make this integration dimensionless. Okay, whether you say the relation between time period, or relation between time period and amplitude, or relation between time period and energy, both things are equivalent, because if at extreme point, this is one extreme point and my amplitude is x plus, okay? So your total energy at x plus will be k x plus power 2n, because at extreme point your kinetic energy is 0, therefore your total energy is equal to this. And at all points, you see, all points throughout the motion, the total energy will be same because this is a constant. And at extreme point, this is exactly equal to kx plus to the power 2n, as at the extreme point or turning points, your kinetic energy of the system is 0. Okay. Now, if I find a relation between t and x plus, it is equivalent to finding a relationship between T and E. Why? Because your x plus, you can express it in terms of E. That is, your x plus will be E by k to the power 1 by 2n. Therefore, finding a relationship between time period and amplitude is equivalent to finding a relation between time and energy. In some questions, they ask the relationship between time period and energy also. Both are equivalent thing. Okay. Now, so if we find the relationship between T and E here, then we'll substitute back to get the relationship between time period and amplitude. But before solving this integral, the question is how to carry out this integration, because here inside E is there. So somehow I have to pull out this E out of this integration and ensure that whatever remains inside the integral, that will remain independent of E. What I'm saying, here E is there. Now let me somehow pull out this E out of the integration and ensure that the integration in the integral is independent of E, so that whatever outside the integral, that will represent the dependence of T and E. Okay. In order to do that, what we have to do, we have to non-dimensionalize this integral. Okay. Non-dimensionalize. That means here integrand E minus kx to the power 4, they have the dimension of energy. Somehow I have to bring this dimension factor outside the integral and make this integral a non-dimension thing, so that when I integrate that, I will get a number only, and whatever the coefficient, that will represent the dependence with energy. Okay. So how can I do that? For that, let me substitute x equal to some x plus times u. U is a variable, dimensionless variable. Okay. This kind of substitution I will do, because if I do that, what will be the range of u when x is 0? When x is 0, what will happen to u? U also will tend to 0. Okay. When x will go to x plus, what will happen to u? U will go to 1. Okay. Now u is here, this case, u is x by x plus. And you see, this is the ratio of two distances. Now the parameter u is dimensionless. Okay. So what about du? What about dx? Dx will be x plus. Dx will be x plus du. Okay. Dx will be x plus du. And I know in terms of energy, my total energy is E equal to k x to the x plus to the power 2n. Okay. Sorry, here I have put 4. Actually, we are doing it for a general system, that is x power 2n potential. So let me put it 2n here. Okay. I will put 2n here, and finally we will find the relationship for x to the power 4. Let us calculate for a general case. Okay. Now E will be kx plus to the power 2n, and this is the total energy which is a constant here. Now, if I substitute this there, what I will get? This right hand side is t by 4. Sorry, left hand side is t by 4. 0 to, now the limit changed from 0 to 1. Okay. Now this 2 by m factor I can carry out outside, that is m by 2 square root. M by 2 square root dx is x plus du. X plus du, and e I can substitute k x plus to the power 2n minus k x to the power 2n whole power half. Now, if I pull out k x plus power 2n, so I supposed to write it in terms of u. Okay, so if I this will be k x plus to the power 2n into u to the power 2n. If I substitute x as x plus u. Okay, now when I pull out k x to the power 2n, 1 x plus is there in the numerator, so what I will get, that is this k is half, so this I can club with this constant m by 2k square root x to the power, here 1 power is n, so when it will go to top, this will be x plus to the power 1 minus n, 1 minus n du square root of 1 minus u to the power 2n. Okay. Why? Kx plus I have taken common, pull out of the integral. So x plus to the power 1 minus n du divided by 1 minus u to the power 2n. Now you notice one thing, this integral here, this integral only depend upon u. What is u? U is the ratio of x by x plus. It is a dimensionless number. And what is the limit for u? It is simply a number, 0 to 1. So when you integrate this, it is ensured that the result will not depend upon energy. This will simply going to give you a number. We may not know that number. Right now, we don't know that number. But one thing is sure, the result of this integration is going to be a number only, which will not depend upon either x plus or on e. This will not depend upon that. This is simply going to give you a number only. Therefore, the dependence, whatever we got here only. So this t will depend upon x to the power 1 minus n only. Okay, because this factor is not going to contribute for amplitude. So the dependence what we got is t will go as x plus to the power 1 minus n. But sometime nowadays what I have seen is in some questions, they not only ask this power dependence, but also they ask this coefficients. So in that case, what we have to do, we have to carry the integration and find the result. Okay, because if they simply ask you what is the dependence of t on x plus, okay, you need not to carry out this. But if they ask you what is the proportionality constant here, in that case you have to integrate. In our problem, what we are solving, they don't ask that. They simply asking the dependence. So we don't need to carry out the integration. But as a factor of safety, let us do this integration and find the proportionality constant also. Okay. So we can do this. This is a standard integral form. Okay. How to do that? Let us see. So this is du by 1 minus u to the power 2n square root 0 to 1. Now you substitute u equal to sine theta. If you substitute that, u equal to sine theta power n you substitute. Okay. So that the u to the power 2n will be sine square theta. Sorry, u to the power n you substitute as u to the power n substitute as sine theta. What about u then? U will be sine theta to the power 1 by n. What about du? Du will be, okay, from here let me calculate. So u to the power n minus 1 du will be cos theta d theta. So du will be cos theta d theta divided by u to the power n minus 1, and u to the power n minus 1 will be sin theta to the power n minus 1 by n. Okay, therefore this is cos theta d theta divided by sin theta power n minus 1 by n. Now, what about the limits? This is from 0 to 1. When I say this sin theta, the limit will go from 0 to pi by 2. Because theta is 0 when u is 0. And is there any question at this point?
So there should be an n at in the n factor also. Sonal is telling, sir. There should be
Where?
a factor of n also. In the denominator it will come, I think, sir.
Where n?
Du is equal to cos theta d theta by n into u power n minus 1.
Yeah, thank you. Here there will be n. Okay. N into u to the power n minus 1. So here it will be n. So when you differentiate, this is n u to the power n minus 1 du cos theta d theta. Okay. Now if I substitute it there, what will happen? Du, that is cos theta d theta n sin theta to the power n minus 1 by n. And what about this 1 minus u to the power n? That will be simply cos theta. Okay, because cos theta and 0 to pi by 2. So this cos theta get cancelled. 1 by n I can take out. So this will be 0 to pi by 2. And if this I take out, this will be sin theta 1 minus n by n d theta. Okay. Now, if you remember from your mathematical physics, we have standard integrals, beta integrals, whose general form is, if you say beta of p and q, that is twice of 0 to pi by 2 sine of sin theta to the power 2p minus 1 cos theta to the power 2q minus 1 d theta. Okay, this is standard beta integral. Now our integration is somewhat like this. Okay, here instead of cos theta, we don't have cos theta term. That means my 2q minus 1 is 0 because there is no cos theta term. So 2q minus 1 is 0. That means q is half. And what about 2p minus 1? 2p minus 1 is 2p minus 1. If you compare this with this standard form, you will get 2p minus 1 is 1 minus n by n, that is 1 by n minus 1. That means what is p? P is 1 by 2n. So this integral is nothing but beta of 1 by 2n and half. And of course, I have to multiply 2 here and divide 2 here. So that this whole thing will represent a beta integral. Okay. Therefore, I can write this as 1 by 2n, 1 by 2n, beta of my p is 1 by 2n. What about q? Q is half. Okay. Therefore, this
Where is
integral.
cos theta term, sir? Cos theta.
No, that is what I am saying. This you can think of. There is no cos theta term. You can think of cos theta to the power 0 d theta. Correct?
No, sir. In the previous step, sir, there's cos theta, no, sir. Previous. That
This step you are saying?
yes sir, yes sir.
Because when you substitute 1 minus u to the power 2n, that is
Yes,
u
yes sir.
1 minus sine square theta, that is cos theta. Okay.
Yes, yes sir. Yes sir. Thank you sir.
Okay. So this is what we got. Now, what is my time period there? Time period is t by 4 is equal to. Can anyone remember what was the coefficient I have written? I forgot actually, and I know where I have made any notes. Can you tell me? This thing I forgot. Anyway, the integral part is 1 by 2n beta of 1 by 2n half. What was the coefficient? Can anyone have written down that? Please tell me this factor. Some m by 2k something was there, no?
Yes sir. Root of m by 2 into x plus power 1 minus n.
Root of m by 2k x plus to the power 1 minus n. Is it so? Yeah? Hello?
Yes sir, yes sir.
Okay. So this is that implies t will be, if you take this 4 to that side, this will be 2 by n m by 2k beta 1 by 2n half x plus to the power 1 minus n. Okay. This is the relationship between time period and amplitude. If we want to write in terms of time period and energy, what will happen? We know E is k x plus to the power 2n. So what about x plus then? X plus is e by k whole to the power 1 by 2n. So if I substitute it there, what will happen? 2 by n m by 2k beta 1 by 2n half e by k 1 minus n by 2n. This is the relationship for time period with energy. Okay. Now in our case, you see, our case, the amplitude they have given x plus is a, and what about the power? 2n is 4 here. Okay, that implies n is half, n is 2. Therefore, when you substitute it there, what will happen? Your time period will go as n is 2 here. So how it will depend upon amplitude? A power minus 1, because when you put n equal to 2 here, 1 minus 2, that is minus 1. What about energy dependence? Energy dependence, this will be 1 minus 1, 1 minus 2 minus 1 divided by 2 into 2 minus 1 by 4. This will go as e power minus 1 by 4. Okay. Now, there are some simple cases where we know already the result, and we'll use that to check the consistency of our formula. For example, when we have a harmonic oscillator. In case of harmonic oscillator, we have our potential V of x as half m omega square x square. Okay. Therefore, this case, my 2n is 2, and that implies n is 1. If I substitute that, what I will get, t is independent of x plus, because 1 minus 1 is 0. This is also independent of energy. This is a well-established fact. We know in case of simple harmonic oscillator, the time period is independent of energy and amplitude. it does not matter how big is your amplitude is. The time period in each case will be same. This is one peculiar feature of harmonic oscillator, and our formula also is consistent with that result. Moreover, when you go a Kepler potential, that is inverse square potential, inverse square force potential, where your V of R will go as 1 over R. This case, your 2n is minus 1. That implies n is minus half. So if you substitute it there, what you will get? Your t will go as x power 3 by 2. Because 1 minus half, that is 1 plus half, 3 by 2. X plus power 3 by 2. And this is famous Kepler's law. Okay, which says the square of the time period is proportional to cube of the amplitude, and this is consistent. Our formula is consistent with that. Okay, so whatever we have derived, that is correct. Now there is a question for you. You see, whatever analysis we have done it for one dimension. In one dimension, we have found the time period amplitude relation. Now, this case, the Kepler problem, the Kepler potential, the particle moves in 3D. But however, still in that case also, our formula works. Even if the particle is moving in 3 dimensions, the formula gives correct result. My question is, why is it so? So I am asking you, in case of Kepler potential also this works. Why is it so? What we have derived, that is for one dimension case, but in case of Kepler problem also it works. Why is it so? Any one of you wants to tell? Anybody of you? You can type in the chat box also. Is my question clear to you, or any doubt in that? You have any doubt in the question? Okay, so you can think this problem. Anybody? Okay. So do you have any problem, at least in this problem? Do you able to follow this problem, or any doubt? At least you say yes or no. Do you understand this problem, or any doubt in this problem?
Yes, sir, it is clear.
Do you follow?
It's clear.
Yes, sir.
Yes, sir. But max is little bit tough, sir.
Where do you have problem? We can discuss. You have to tell no. Math. At which point you have any doubt?
Sir, we considered that means I didn't understand how that beta came, sir, in between.
Yeah, that is what. See, like beta and gamma, they are standard integrals. Okay, they have specific form. That is, when I say some beta of PQ, beta is a standard integral. It has defined, by definition, beta of PQ is defined as, beta of PQ is defined as 2 times 0 to pi by 2 sine theta of 2p minus 1 cos theta of 2q minus 1. This is the definition of beta function. Okay, this is one of the representation of beta function. There are other representation also. Why I am writing this representation? Because this is required in our case. Okay, this is standard representation of beta function. Now, in our case, we got a function like this, that is 0 to pi by 2, 0 to pi by 2 sine theta to the power 1 minus n by n d theta. Okay. Now, my aim is to write this integral in terms of a beta function. How can I write that? Here you see, to write it in the form of beta function, one thing is there, my limits are same. It is 0 to pi by 2, and here also it is 0 to pi by 2. There is no doubt, there is no problem in that. Here 2 factor is not. That I can do anyway. I can multiply 2 and divide 2. So two things I have sorted out. That is this 2 factor. Second thing, the limit, which is already same. One more problem is there. I don't have cos theta term here. So how can I write? Cos theta term is not there, means I can write it as cos theta to the power 0 d theta. Now you compare, I want to find this corresponds to beta of what? And this corresponds to beta of what? Now here 1 minus n by n, if you compare, this is equal to 2p minus 1, because that is the power of sine theta. And this case, cos theta power 0. This 0 equal to 2q minus 1. Okay. If I find the value of p and q, that will give me the beta function value. Okay, pq value. So if you compare that, this 1 minus n by n equal to 2p minus 1. If you solve this, what you will get? P is equal to 1 by 2n. What about other? This is 2q. 0 is equal to 2q minus 1. That implies q equal to half. So this integral is equal to beta of p. P is 1 by 2n. And what about q? Q is 1 by 2. That is why instead of that integral, I have replaced this by a beta function. What is the advantage of replacing it by a beta function? Beta, because beta function has a relation to gamma function, and from that we can evaluate the value. Okay? That is why I have written it in terms of beta function. If you don't want to write in terms of beta function, you can just keep it as a integral only, because one thing is ensured that the value of the integral is not going to be a function of energy. Okay, this is what I have done.
Yes, sir. Now it's clear.
Is it okay now?
Yes, sir.
Okay. So any other doubt at this moment? Any other doubt? Okay, so let me move ahead. Let me write Lagrangian equation. After that, we'll solve few problems on Lagrangian. Okay. So in the last class, Sir has derived the Euler-Lagrange equation from D'Alembert's principle. So what is that? The Euler-Lagrange equation for a conservative system. That is, what do we mean by conservative system? That is, the energy of the system is not going to change. So for a conservative system, the Euler-Lagrange equation, in the last class we have seen that d by dt of del L by del qk dot, okay, k is just a number. It is the index for your generalized coordinate. It can be a number from 1 to n if you have n generalized coordinate. So d by dt of del L by del qk dot minus del L by del qk equal to 0, where k goes from 1, 2, 3 up to n. And for conservative system, we have seen this n is called Lagrangian for the system, and this value is equal to T minus B. This is the difference in kinetic energy and potential energy. This we have seen. Okay, this is the Euler-Lagrange equation for a conservative system. Now you notice one thing. So for each generalized coordinates, that is Q1, Q2, Q3, Q4 up to Qn, for each generalized coordinates, correspondingly you have a differential equation. So for each generalized coordinates, we have one differential equation. So to find each generalized coordinate as a function of t, what you have to do, you have to integrate each differential equation. Okay? Differential equation. So how many differential equations we have? We have n second order differential equation. Why? Because this is one derivative with respect to time, another derivative with respect to qk dot. So we have n second order differential equation. So if you have n second order differential equation, how many boundary conditions you need? You need to solve the system completely. You need 2n initial conditions or 2n boundary condition, because you have n differential equation and each equation is a second order differential equation. So total initial condition you need is 2n, 2 into n. Okay. So second order differential equation. And the Lagrangian of the system in this case, see, in general, this is a function of x dot and v is a function of x. And in some cases, we can have also function of velocity also, potential is also a function of velocity. Those are called velocity dependent potential. Okay. So in general, here L will have only terms qk and qk dot. We don't go up to higher order of derivative of generalized coordinate. That is, the Lagrangian does not involve any higher order derivative like qk double dot or qk triple dot or so on. So we are only dealing with qk and qk dot. Therefore, the Lagrangian is a function of your generalized coordinate, that is qk and qk dot. What is qk dot? Qk dot is generalized velocity and time. So qk is generalized coordinate, qk dot is generalized velocity, and t is time. The Lagrangian may have a explicit time factor or may not have a explicit time factor. So what will be the consequence for that? We'll see. Okay. In general, it is a function of generalized coordinate, generalized velocity, and a time. Okay. This is the Lagrangian. Now, when you take the partial differentiation of this Lagrangian with respect to qk, any generalized coordinate, you will get the derivative of generalized momentum, that is pk dot. Okay. And what about del L by del qk dot? These things I am not going to the derivation of this. We'll see in the next class. But for solving problems, I need at least these relations, that is, I am noting it down here. Del L by del qk is pk dot, where pk is the generalized momentum. and del L by del QK dot will give you generalized moment. Now, when we talk about Lagrangian, we talk about cyclic coordinate. What do we mean by cyclic coordinate? Cyclic coordinate is a coordinate which coordinate is a coordinate which does not appear in the Lagrangian. That is, the Lagrangian will not depend on that particular coordinate. Like here, as I have said, suppose I have n generalized coordinates q1, q2, q3 up to qn, and let us say in that one generalized coordinate qk, on that this Lagrangian does not depend. In that case, this qk is called a cyclic coordinate. Okay, what will happen if a coordinate is cyclic? Then immediately I can write, if a coordinate is cyclic, then del Ly del Qk. That is, as this Lagrangian is independent of this Qk, when I take this partial differentiation with respect to Qk, this will give me 0. Right? But I know from definition, del L by del Qk is Pk dot. That implies Pk dot is 0. If Pk dot is 0, what about Pk? Pk will be a constant independent of time. So we'll call it as a constant of motion. That means the momentum is conserved. What is the conclusion? The conclusion is, if a coordinate is cyclic, the corresponding momentum is conserved. Conserved means it is not going to change with time. Okay. So the conclusion is, if a coordinate is cyclic, then corresponding momentum is conserved. This is the conclusion. Okay. Now let us take a simple problem and solve. We start with first free particle. Free particle in one dimension. This is the simplest case one can think. Okay. So let us start with a very simple case, that is free particle in one dimension. So for a free particle, what will happen to your potential energy? V of x is 0. Potential energy is 0. So for a free particle, the potential energy is 0 because there is no force acting on it. So whatever the free particle, the total energy of the free particle essentially is due to its kinetic energy. So what will its kinetic energy then? It will be half m x dot squared. Then what about the Lagrangian? The Lagrangian will be t minus b, that is equal to half m x dot square. Okay, because b of x is 0. Now we have only one coordinate, that is x. So how many differential equations we will have? We will have only one differential equation. Okay, because I have only one generalized coordinates. So how to write the differential equation? I know the differential equation is d by dt of del L by del Qk dot minus del L by del Qk is 0. In this case, my Qk is x. I have only one generalized coordinates. Okay. So what about del L by del x dot? Del L by del x dot that is equal to del by del x dot of half m x dot square, that is m x dot, m x dot. What about del n by del x? Del n by del x, there is no x dependence here, so x is cyclic. What will happen? Del n by del x, that is 0. So if I substitute these two there, what will happen? D by dt of what is del n by del x dot, that is mx dot, mx dot minus 0, that is equal to 0. Okay, so d by dt of mx dot, this is total time derivative, that is mx double dot, that is equal to 0. Okay, so what is x double dot? In Cartesian coordinate, x double dot is equal to your acceleration. So mass times acceleration is equal to 0. That means net force acting on the particle is 0. That is what we know for a free particle. Free particle, the force acting on it is 0. So essentially, the Euler-Lagrange equation gets reduced to the Newton's equation. So in whether in Newton's equation or in Euler-Lagrange equation, final physics is same. It is not different. How to solve mx this equation, that is another story. Okay, but if you apply the Euler-Lagrange equation, you will get back to equation which is equivalent to Newton's equation. Okay, so the physics in both formalism, whether it is in Newtonian mechanics or in Lagrangian mechanics, in both cases it will be same. It is like two different representations only. Okay, so this is essentially Newton's equation. You can solve this equation to find the position as a function of time and velocity as a function of time. Okay, this is for free particle. Let us take another system and solve. We'll solve this for harmonic oscillator now. We solved for a case where there is no potential energy. Now let us solve this for a case where we have a potential energy, and we'll consider the simplest case for a harmonic oscillator in one dimension. We'll start with simple problems, then we'll go to some difficult problems. So, harmonic oscillator. Simple harmonic oscillator in one dimension. So for a harmonic oscillator, what is my kinetic energy? Kinetic energy is half m x dot square. Whatever the potential energy, this case is half m omega square x square. So the Lagrangian for the system will be half m x dot square minus half m omega square x square. Is not, this is t minus b. Now I have here only one generalized coordinates. Okay, so when you solve the equation of motion using Euler-Lagrange equation, your first step is to set up the Lagrangian for the system. To set up the Lagrangian for the system, what you have to do? First, you have to identify the kinetic energy, identify the potential energy, then you take their difference, that will represent the Lagrangian of the system. Okay, of course, before finding the kinetic energy and potential energy of the system, you have to choose a suitable coordinate system. What is your generalized coordinates, that you have to identify. That is a bit tricky business, but if you keep on solving problems, you will have an idea how to choose what will be the generalized coordinates for what kind of problem. That will have idea, that will come with experience. Okay, this is a very simple problem. Here we don't need to bother about that. Here simply x is the generalized coordinate. But in some cases, the main trick is how to identify the generalized coordinate. Once you find the generalized coordinate, then you set up the Lagrangian, set up the kinetic energy for the system, potential energy for the system. From that, you find the Lagrangian. Once you find the Lagrangian for the system, then you go to find the Euler-Lagrange equation for the system. Okay. This case, the Lagrangian is half m x dot square minus half m omega square x square. So what will happen to del L by del x dot? These terms I need to find because these terms are involved in the Euler-Lagrange equation. Okay. So what is del L by del x dot? Del L by del x dot is m x dot. Okay. So what about del L by del x? Del L by del x is minus m omega square x. So if you substitute it in the equation d by dt of del L by del x dot, del L by del x dot minus del L by del x equal to 0, that is d by dt of m x dot minus this minus becomes plus. So m omega square x equal to 0. That implies x double dot. If I divide this m, what I will get? X double dot plus omega square x equal to 0. This is the Euler-Lagrange equation for Euler-Lagrange equation for simple harmonic oscillator. How to solve that? That is another story. Okay. This case, this is a second order differential equation, homogeneous second order differential equation. The solutions of this will be in cosine and sine terms. Okay. I am not going to solve this equation right now. My only interest is to find the Euler-Lagrange equation. How to solve this equation to get x as a function of time, that is another story. We'll do that. But in this problem, I'm interested only finding this differential equation. Okay, this is the Euler-Lagrange equation for a simple harmonic oscillator. If you want to solve this equation, what will happen? You see, this is a second order homogeneous differential equation. If you solve this, what you will get? X at some a of cos omega t plus b of sin omega t. Now you use appropriate boundary condition to find the value of a and b. Okay. In general, the solution will be of this form. Okay. Now let us ask a question: whether the choice of Lagrangian for a given system is unique or not. Anyway, one thing is sure. See, when you write the Euler-Lagrange equation for any system, this is unique. This x double dot plus omega square x, that is always unique. That is not going to change. That is always will be same. For once you fix the system, if you consider for harmonic oscillator, your Euler-Lagrange equation will be always x double dot plus omega square x equal to 0. But now my question is whether the choice of Lagrangian for a given system is unique. What I mean by this, that is here this case my Lagrangian is half m x dot square minus half m omega square x square. I am asking whether this value half m x dot square minus half m omega square x square, whether this is unique. This is unique for harmonic oscillator, or I can find any other Lagrangian which also give same Euler-Lagrange equation. If that is the case, then the Lagrangian is not unique. But if it is unique, the Lagrangian for harmonic oscillator, this is fixed. I cannot find any other Hamilton, any other Lagrangian which will give rise to same Euler-Lagrange equation. So I am asking whether the choice of Lagrangian for a given system is unique or not. What do you think?
No, sir.
Why?
So we can choose a different coordinate system and we can get the different Lagrangian, and again by calculating we can get the same result.
Now, can you repeat what you are saying?
So I am saying that we can go to the different coordinate system and we will get a different Lagrangian, and after calculating we will get the same result.
Okay, see, the equation will be same. What I am saying, the value, you may here I have written it in one dimension, so it does not matter. Suppose I write a Lagrangian half m x dot square plus y dot square minus b, let us say, is equal to some k x square plus y square. This is the Lagrangian for a two-dimensional system. Now, the same thing which I have written it in Cartesian coordinate, the same thing I can write this in polar coordinate also. If I do that, what I will get? I will write this as half m r dot square plus r square theta dot square minus k r square, because in polar coordinate your x equal to r cos theta, y equal to r sin theta, r sin theta, r sin theta. Okay, so if you substitute that, this is the same Lagrangian in another coordinate system. Okay, the form of the Lagrangian is different. Okay, I am not asking this. Okay, what I am asking, even if, see, this case, one Lagrangian is in Cartesian coordinate, another Lagrangian is in polar coordinate. But in both cases, the value of the Lagrangian is same. For example, you consider in one case, this case, the Lagrangian, that is T minus B, let us say is 50 joule. If you convert this to some other coordinate, the value is same. Okay, you are just using different coordinate. This case, this is x and y. In other case, this is r and theta. But the value, numerical value of the Lagrangian is same. Okay, this case this was 50 joule, and this case also it will be 50 joule. The only difference is you are re-expressed your Lagrangian in some other coordinate. But in both cases, the numerical value of the Lagrangian is same. And if you, whatever you said, that is correct. If you solve this, and you will get same type of equation. Okay, you will get x and y in terms of time, and here r theta in terms of t. If you reconvert, you will get one from another. That is not a problem. I am asking, what my question is, can you have different Lagrangians? That means you consider, you forget about different coordinate system. In the same coordinate system, can I have two different Lagrangian? Two different Lagrangian means the numerical value of the Lagrangian will be different. That is, in one case it is 50 joule, another case it is 60 joule. Okay, can I have such a Lagrangian? My question is, are you getting? Roshan, are you getting my question? What I am asking?
Yes.
Hello?
Yes.
Your voice is not audible. Can you?
Hello. Yes, sir. I'm getting you. Yes, sir. I'm getting you.
What you said?
Yes, sir. Hello.
What you said? You said the Lagrangian is two different coordinate system. That is fine. But I am not asking that. I am asking, suppose in one case your Lagrangian is say f of x. In another, f of x and x dot. In another case, I will get some other different function, g of x dot. Is it possible? If this is possible, then the Lagrangian for the system is not unique. If I cannot find another function g, then the Lagrangian is unique. So my question is with respect to that, not with respect to coordinate system. That freedom we will always have. You can always go from one coordinate to others. coordinate. Cartesian to cylindrical or cylindrical to Cartesian, Cartesian to spherical polar to elliptic, whatever it is. That freedom will always have. I don't have any problem in that. If you do the coordinate change, the numerical value of the Lagrangian will remain same. That is not going to save. But my question is, do you have any different functional form? Like you have one function f of x dot. Can you find another function g of x and x dot where both these will give rise to same Euler-Lagrange equation? This is what my question.
Sir,
Is the question clear to you? What I am asking?
Yes, sir.
What do you think?
sir, we can multiply the Lagrangian with any constant factor. For example, any constant number.
Yeah, that is trivial case. That thing you forget. Okay, suppose you have L, you multiply some alpha times L, and this alpha is independent of x, x dot, q dot, and t. In both
Yes,
cases, you will get same differential equation. That is fine. This case you don't consider. Other than that, this is just because this case, this Lagrangian, these two Lagrangians are not linearly independent. They are linearly dependent. Okay, so you forget this case.
Okay.
What you said correct, but you discard this case. Other than that, anybody? You can speak. Whether it is right or wrong, that does not matter. Speak. What do you think?
So, sir, we can add a term which is independent of velocity and the coordinate. That again, the Lagrangian will be the same.
Why?
So, because by differentiating it with respect to coordinate or velocity, the result is not going to change.
Yeah. So what you are saying? Suppose.
So we can add a quantity, a term which is independent of velocity and coordinate. Respect to which we. Yes, sir.
Independent of velocity and coordinate, both.
Yes, sir.
That is also a trivial case. Whatever Farid has told, same thing. Suppose your L prime is L plus alpha, some constant, and this is also a trivial case. Okay, so that is fine.
Okay.
So I am not interested in that, whether it is you multiply with alpha or you add some constant, because see, when you add this alpha, you say this A is T minus V plus alpha, correct? And you know this potential energy is always, when you define the potential energy of the system, that is always with respect to some reference point. For example, suppose you have a ball here. You have a ball lying on a table whose height is h. Now, the potential energy of this ball will be, if this height is h, and if you consider this as your reference point, the potential energy will be, this case, mgh. Now, in the same case, if you consider your reference point to here, you just shift your reference point, your potential energy becomes 0. Okay, therefore, this alpha factor, that constant factor, you always can discard. You can choose. You can shift your reference point to nullify that alpha. Okay, because your potential energy is a reference dependent. Okay, you can choose your reference point so that you can nullify that alpha. So this alpha you can ignore. Okay, without alpha, without adding any constant or multiplying any constant, can we find a Lagrangian which will give rise to same Lagrange equation? This is my question. Okay, what you said correct, but let us forget that case. That is trivial case. Okay. Are you getting Rakesh, Roshan?
Yes, sir.
Okay. Yeah, that is possible in this case. Like in electricity magnetism, we have seen we can change our electrostatic potential, scalar potential, and vector potential in such a way that they will give rise to same electric and magnetic field, in the same manner, we always have a freedom to change our Lagrangian to get to, we can have two different Lagrangian to get a same kind of equation of motion. That is called the gauge freedom of Lagrangian. Okay, gauge invariance or gauge invariance, gauge invariance of Lagrangian. That is, suppose if you are, when we are total time derivative, total time derivative, total time derivative of a function, total time derivative of a function, which is function of generalized coordinate, generalized coordinate and time. Okay, not generalized velocity. You have to remember this. If you add to your Lagrangian the total time derivative of function, which is a function of generalized coordinate and time only, in that case, the Euler-Lagrange equation is not going to change. Euler-Lagrange equation will remain unchanged. This is called gauge invariance, remain unchanged. Now you define a function f, which is a function of, as we defined, this is a function of only qk and t. This is not a function of qk dot. This is only function of generalized coordinate and time. So in such case, if you define your new Lagrangian as L prime, that is equal to L plus df by dt, in both cases, the Euler-Lagrange equation will be same. They will give rise to same Euler-Lagrange equation of. This is called the gauge invariance of Lagrangian. I am not going to derive this result. Okay, you can try this. So to derive this, what you can do, you write the Euler-Lagrange equation in both cases, for L prime as well as L. Okay. Now for L prime, when you write this df by dt term, so what I'm saying, when you write, see this f, this case is a function of qk and t. It is a function of generalized coordinate and time only. So for L, I know the Euler-Lagrange equation is del L by del qk, del L by del qk, del d by dt of del L by del qk dot minus del L by del qk is 0. Now, my claim is, if I add a total time derivative to the Lagrangian, the Euler-Lagrange equation is not going to change. Therefore, what I have to expect that this must be equal to del, if I reduce that d by dt of del L prime by del qk dot minus del L by del qk is 0. Okay, so del L prime by qk. Now if you substitute L plus df by dt, this will be equal to d by dt of del L by del qk dot plus minus del L by del qk. The f factor I am keeping it separate. Okay, plus d by dt of, because here L prime plus L plus df by dt. So there will be this term d by dt of del f by del qk dot minus here L prime is L plus df by dt. So therefore, okay, see here I have made a mistake. D by dt of del by del qk dot of df by dt. This is total time derivative. Okay, so you have to be careful. This is df by dt minus del by del qk of del by del qk of df by dt. Del by del qk of df by dt. That is equal to 0. Now, if I claim that in both cases the Euler-Lagrange equation is same, then what will happen? This must be equal to this. Okay, but this second term, the L prime, has an extra term. So what do you expect? This extra term must go to 0. So to prove that, what you see, you show that the extra factor d by dt of del by del qk dot of df by dt minus del by del qk df by dt must be equal to 0. If this part goes to 0, then what will happen? In both cases, this L prime and L will give rise to same Euler-Lagrange equation. Okay? This is what called gauge invariance of Lagrangian. That is, if you add total time derivative to the Lagrangian of a system, in both cases, the Euler-Lagrange equation will be same. So the conclusion is the choice of Lagrangian for a given system is not unique. We can arbitrarily change the Lagrangian of a system without changing the Euler-Lagrange equation. Okay, this is the reason. But one thing you notice, in both cases, if we change the Lagrange equation, the Euler-Lagrange equation will not change, but your generalized momentum, that is pk prime, that is equal to del L prime by del qk, and pk del L by del qk, your generalized momentum, they will not be same. They will be different in both cases. Okay. The only difference is Euler-Lagrange equation will not be same, but your generalized momentum, they are going to differ from each other. Only the final equation will be same in both cases. And in fact, from this, if you write the Lagrangian for a charged particle moving in an electromagnetic field, what I'm saying, you write the charged particle, you write the Lagrangian for a charged particle in electromagnetic field. Okay, then as we know, the Lagrangian will have, we can change the Lagrangian arbitrarily by adding total time derivative. This Lagrangian we can add a total time derivative. Okay, from this, the gauge invariance for in electrodynamics actually comes. We can there say that one can change the electrostatic potential, scalar potential, and magnetic vector potential arbitrarily to get same electric field and magnetic field. That freedom comes actually from the freedom of the gauge invariance of Lagrangian. Okay, so this is the idea. The Lagrangian for a system is not unique. One can change this arbitrarily. For example, in the exam, they used to ask questions like this. Okay, we'll solve one question which has been asked in last year's CSIR exam. For example, we have seen the Lagrangian for harmonic oscillator is half m x dot square minus half m omega square x square. For example, if I write another Lagrangian L prime, which is equal to half m x dot square minus half m omega square x square plus some x dot. Okay. Now, if I ask you what kind of system this Lagrangian represents, can you tell me what kind of system does this Lagrangian represent? This case, in first case, we have solved and we got our differential equation as x double dot plus omega square x is 0. Now I have another Lagrangian where it is half m x dot square minus half m omega square x square x dot. My question is, this Lagrangian represents what system? Like this Lagrangian represents a simple harmonic oscillator. My question is, this case, this Lagrangian represents what kind of system? Any idea?
Sir, same harmonic oscillator. Sir.
Why?
Sir, we can use this Gauge invariance in this, and
so
we can say that.
How?
Sir, x and x dot,
Hmm.
our generalized coordinate is x. So,
Hmm.
uh,
See, I have to express x dot as the total time derivative of some function, correct?
yes, sir.
So how can I do that? This x dot, I can write it as, just a minute, my camera. X dot, I can
X
write
square
it.
d
Yes,
by dt of
exactly.
x square.
D by dt of x
X
square.
square.
X square by 2. Correct?
Yes.
So this is my f, and this is total time derivative of x square by 2. Therefore, I expect that in both cases, the Euler-Lagrange equation will be same. And we can verify this. For example, you see. For example, if I want to explicitly find the Euler-Lagrange equation, what will be my del L by del x dot? This case, this is m x dot, and there is also x dot here. So this is m x dot plus x. Okay. What about del L by del x? Del L by del x will be minus m omega square x, right? Now, what is Euler-Lagrange equation? D by dt of del L by del x dot minus del L by del x equal to 0, correct? If you substitute this there, it is L prime, sorry, this is L prime. Now, if you substitute d by dt of m, okay, I have missed one term here. Del L prime by del x is minus m omega square x, and here also you have a term that is x dot. Okay. So m x dot plus x minus this is, that is plus m omega square x minus x dot, that is equal to 0. So when you take the time derivative, mx double dot plus mx dot. Here I made a slight mistake. No mistake. Correct only. This is correct only. Okay. So mx dot x dot plus m omega square x minus x dot equal to 0. So this get cancelled. Finally, what you will get, x double dot plus omega square x equal to 0. Says the Euler-Lagrange equation is same. This case also, this will lead to same Euler-Lagrange equation, and this case also, this is leading to same Euler-Lagrange equation. So this is called the gauge invariance of Euler-Lagrange equation. Let me write one question here, which was asked last year CSIR. I think I have
Sir, there's a question on YouTube, sir.
Sorry?
Sir,
Sorry?
there's a question on YouTube, sir.
Yes.
There was a question on YouTube. He has now deleted it. He was asking only after we solve the equation, we call it a system, something like that. He had said, sir. Just now it came as message retracted.
Okay, no problem. So if he or she is attending leave also, he can ask if there is doubt. Okay. So I have noted down that problem somewhere, which was asked in CSIR. Let me check. Yeah, I got that. Okay, so the question is like this. So I was asked in, I think, 2019 December somewhere. The question is, which of the following terms, which of the following terms when added to the Lagrangian L x y x dot y dot. This is a two-dimensional Lagrangian, okay, of a system with 2 degrees of freedom. 2 degrees of freedom will not change the equations of motion. This is question, I think, if my memory is correct. This is in CSIR 2019, maybe June or December. I don't know properly. Just one of my students asked me. So that is not important, but this was asked in CSIR. What are the options? The options are x dot minus y double dot to x y double dot minus y x double dot b x y dot minus y x dot for each y x dot square plus x y dot square. So what do you think? Same way we have to proceed. But what you have to check, you have to just check out of these 4, which you can express as total time derivative of a function, which is a function of x and y only. Okay, that you have to check. Okay. I'm leaving this as an homework for you. You can try this and you tell me the next class. So let me solve. How much time I have? 10 minutes is there. So let me solve one more problem, and with that I will conclude. Okay. So let me solve. This is trivial also. Simple pendulum. So in case of a simple pendulum, when we solve systems using Lagrange, our first step is to set up the Lagrangian for the system. Okay. Now you consider a pendulum inextensible, which is connected through an inextensible string of length L. And let's say the pendulum has a mass M. And I am considering this as my reference point. So if this angle is theta, so what will be my this distance, that is L cos theta. So my potential energy is below the reference point. So what it will be? My Vx will be minus mgl cos theta. Minus mgl cos theta. So what will be the kinetic energy? The kinetic energy will be this distance. Okay. Actually, if this is the mean point, this distance, if you compare with a square, with a circle, this will be L theta. If this distance is x, this is, you know, x by L is in this triangle, x by L will be theta, that implies x is equal to L theta. If I consider theta as my generalized coordinate and I want to write the equation in terms of theta, then x will be L theta. And what is kinetic energy? That is half M x dot square, that is equal to half m L square theta dot square. Okay, half m L square theta dot square. Now, when I write the Lagrangian will be half m L square theta dot square minus plus mgl cos theta y plus, there is already a minus sign. When I subtract this, this will be half ml square theta dot square plus mgl cos theta. Now, what is del L by del theta dot? That will be ml square theta dot. What is del L by del theta? That is minus mgl cos theta. So if I substitute that in Euler-Lagrange equation, that is d by dt of del L by del theta dot minus del L by del theta, that is equal to 0. So what do I have? d by dt of del L by del theta dot, that is m L square theta dot minus del L by del theta. Del L by del theta is minus mgl. This will be sin theta, because when I take differentiation with respect to cos theta, this will be, I have made mistake somewhere. This is minus mgl sin theta. Okay. So this is minus, again minus, that is plus mgl sin theta is equal to 0. That implies if I divide ml square everywhere, we will get theta double dot plus g by l sin theta equal to g. Okay. This is the Euler-Lagrange equation for simple pendulum. This, in fact, this we have done in the previous class. The same equation we have arrived using Euler-Lagrange equation in a very sophisticated way. And we have arrived this equation in the previous class using D'Alembert's principle, and in this case we arrived using Euler-Lagrange equation. And how we solve this equation, that is different story. We do for small angle approximation, we consider theta is very small. In that case, we consider sin theta is nearly equal to theta, and we solve this differential equation, and we find the time period in that case will be equal to 2 pi L by G. Okay. How we solve that equation and all, that is different story. But this is what the Euler-Lagrange equation for simple pendulum. In case of small angle approximation, we will consider theta is much smaller, so sin theta will be even smaller, and we can compare it to theta. And that case, theta double dot plus g by L theta is equal to 0. And the time period what we will find, that will be equal to 2 pi L by G. Okay. This is the case for simple pendulum. So let me ask you one question. Suppose I don't do this small angle approximation. I don't do this small angle approximation. That means I don't consider theta to be very small, and I want to keep this sin theta there. Okay. I don't do this small angle approximation. Okay, if I do small angle approximation, that is theta is very small, I have seen the time period t is independent of the theta. That is, it does not depend upon theta. So time period is independent of theta. Now my question is, suppose I said the theta is not very small, rather I want to keep it as sin theta. So the question is, how time period will depend on theta. What do you think? With increase of theta, whether time period will increase or decrease? Suppose I don't consider the small angle approximation. Now I'm asking whether time period will increase if theta will increase or it will decrease. What do you think? Or it will remain unchanged? If theta increases, what
Sir,
will
I
happen?
think it will increase, sir, time period.
Why?
Or only small angle only time means this equation is valid, right?
Yes. So
So for larger angle distortion, something like that.
this.
I don't know properly, sir.
That is correct. What you are saying from physical intuition, that is correct. Because suppose you have a pendulum like this, and if you move more theta, obviously it will take more time to complete one oscillation, right? So that case, your time will be more, and the time period will that case depend upon theta. And if theta is more, the time period will move. So there is a relation actually, the dependence of t with theta, that is called your Bernoulli's approximation. What is that? That is 2 pi L by G into 1 plus theta square by 16 plus all higher terms. Okay, this is called your Bernoulli's approximation. Okay. So if theta is very small, if you ignore this theta square term, then this is simply 2 pi L by G. And if you consider higher and higher theta terms, then this will depend upon the first correction to this is theta square by 16. Then it will come another term. It is like that. Okay. This approximation is called Bernoulli's approximation. One can derive this. Let me give you a hint how to derive this. You can try this as a homework. Okay. So if you are unable to do, I will help you, but at least you give it a try. So how to derive this? You see, for simple pendulum, the differential equation what we got is theta double dot plus g by l, theta g by l sin theta is equal to 0. Okay. Now theta double dot is minus g by l sin theta. Okay. In both sides, you multiply theta dot. If you do that, that is minus g by l theta dot sin theta. What I have done, I have multiplied theta double dot on both sides. Okay. Now this theta dot and theta double dot, I can write this as d by dt of half theta dot square. Okay. That is equal to minus g by l. This I can write it as d by dt of g by l, as g by l. I have written this is cos theta. So if you take to one side, what will happen? d by dt of half theta dot square plus g by l cos theta equal to 0. Okay. Now as d by dt of this term is 0, so half theta dot square plus g by l cos theta is equal to constant. Okay. For simplification, this constant you can equate it to, you can write this in terms of some cos theta. Okay. So let us say this constant equal to some cos of theta 0. Theta 0 is the initial angle where you have started. So this constant, as this is a constant, I can equate it to some constant cos of theta 0. G by L cos of theta 0. So if I do that, half theta dot square is equal to g by L cos of theta 0 minus cos theta. Okay. So what is this half theta dot square? If you take to that side, theta dot will be 2g by L square root cos of theta 0 minus cos theta. Cos of theta 0 minus cos theta. Theta 0 is like, see, Suppose you have a pendulum here and you drop the pendulum from this position, this maximum angle from where you are dropping the ball, that is theta 0. Okay, theta dot is d theta by dt. So if you integrate, you will get your dependence of time period with theta. So if I write this will be d theta by square root of g by n cos of theta 0 minus cos theta equal to dt. Now the same trick what we have followed in the beginning of class, we'll follow that. Instead of integrating from full, we'll integrate for 1/4, that is 0 to t by 4, and this will be from 0 to theta 0. I'll integrate from this position to this position only. Okay, so this will correspond to 1/4 of the time period. Okay, so if you integrate that, what you will get your t as a function of 2 pi L by g with first correction 1 plus theta square by 16 plus 1 so forth like that. So I am leaving this as an homework for you. What you can do is this cos theta 0 and cos theta, you write it cos theta as theta 1 minus theta square by 2 factorial plus thing, and you consider only these two terms. Same way you write for cos theta 0, then you do some algebras and simplification. Finally, you will arrive this at this region. Okay? Towards end, sorry, I was a bit hurry, but you try this. If you have some difficulty, I will derive this and send you. But remember, the idea is if you increase the theta, the time period will increase. Okay. So, and this relation is called Bernoulli's approximation. Okay. So, if you have
Sir,
any
hello?
doubt, you can ask. Otherwise, yes.
Sir, in the question which you gave us homework, the last question,
Yes.
in which we have to find that Lagrange's item. In that, do we have to find a generalized coordinate in that question?
Generalized
coordinate in that question?
No. Last class or
No, sir. This class.
previous one problem?
Just before you derived the simple
x dot y dot xy that
yeah, that's one.
No, out of 4 options, you check which you can express it as a total time derivative of x and y. You don't.
Okay.
You should not contain any x dot terms. Okay.
Okay.
That you have to check.
Okay. Thank you.
Any other doubt?
Sir.
Yes.
Excuse me, sir. Sir, can you explain that Kepler problem you asked?
Which one?
Few time ago. The Kepler problem. Do you ask?
Which problem?
So the Kepler problem. We derived the equation for.
Sorry.
For one dimension.
Sorry, I'm not able to hear you.
Hello.
Yes.
Hello.
Hello. Roshan.
Sir,
one minute. You are not audible. So could you please put your doubt in chat so that he can read it?
Okay, sir.
Yeah.
Sir, the Euler-Lagrangian equation which we have, sir, is it only for the conservative system, sir?
Yes.
For non-conservative system, sir?
That's right. See, in last class, if you remember, Sir has written one thing. This is for conservative system, but in case of a non-conservative system, the form will be like this: d by dt of del t by del qk dot minus del t by del qk is equal to qk. Okay, in that case, what will happen? The generalized force you cannot express as the gradient of some potential. Okay, for that reason, for non-conservative systems, your Euler-Lagrange equation will be of this form. Okay, but today whatever problems we have solved, they are all conservative systems. So for conservative system, this T you have to replace by L. But if non-conservative system is there, some dissipation like friction and all is there. So this case, your Euler-Lagrange equation will be of this, where Qk is the generalized force. Okay.
Okay, sir.
Any other doubt?
Sir, in the chat box, Roshan has asked, can you explain the Kepler problem you asked? Why it is valid even for the expression which we draw for one dimension?
Yeah, the answer is C. In Kepler problem, even though it is r theta problem, first case we have a central potential which is independent of theta. The potential is central. Second, if you solve this in the case of reduced mass problem, even though it is a three-dimensional problem, the problem will equivalent to reduce a one-dimensional only. Even though the particle is moving in three dimension, because of constraints, it is essentially an one-dimensional problem only. Okay, even though the particle is moving in three dimensions, the problem is essentially effectively the problem is a one-dimensional only. That is why our expression is valid still then. Okay, that is the reason. If you see for a central potential how the Kepler's problem is, because in that case your angular momentum, you have r theta. What will happen for a central potential? Central potential means for a central potential, that is central potential. Sir will teach this, we'll discuss this. For central potential, what is the property of a central potential? Your potential energy is a function of R only. Okay, this is theta independence. If that is the case, the angular momentum, L, angular momentum L, this is a constant of motion of conjugate. Okay, that means for central potential problem, theta is cyclic. If theta is cyclic, in an r theta problem, if theta is not there, you need only one. So the problem is effectively one-dimensional problem. That is why whatever derivation we have done, that is still valid in this case. Okay. So that is the reason why even if the particle is moving in three dimensions, we can still able to apply our formula. Is it okay, Roshan?
Yes, sir.
Okay. So any other doubt? So, is there any other doubt? Okay, if no other doubt, Jogarajan sir?
If there is no more doubt, then we may close the session.
Yes, sir.
Dear students, any points you would like to discuss? Yeah, silence. That means,
No, sir.
yeah. Okay. So, really
If
fantastic.
if you have any doubt, they can put it in the Telegram group. I'll reply. Okay.
Okay, sir.
Okay. Thank you so much for the marvelous session,
Thank you,
Shritikanta.
sir.
Yeah, thank you, students. So, with this, I conclude this session. Thank you.
Thank you.
Thank you,
Thank
sir.
you, sir.
Thank
Good
you,
night.
sir.
Good night, all.
Thank you, sir.
Good night.